Hello friends, and welcome to my channel. In this video we are going to be looking at paper 13 from the May-June 2020 series. For more learning resources you can visit my website waltermess.com. Let's get started with this paper. Question number 1. The cubic equation 7x cubed plus 3x squared plus 5x plus 1 equal to 0 has roots alpha, beta, and gamma. On A, find a cubic equation whose roots are alpha to the power minus 1, beta to the power minus 1, gamma to the power of minus 1. Now, in this case, we want to form a new cubic equation, and I want it to be in terms of y, so I'll say let y be equal to x to the power of minus 1, thus taking the form of the roots as given here. So I'll make x subject, so x is equal to y to the power of minus 1, which is the same as 1 over y. So here I'll substitute y to the power minus 1 for x in this equation. So we'll be having 7 of y to the power minus 1 cubed plus 3 of y to the power minus 1 squared plus 5 of y to the power minus 1, and that's plus 1 equal to 0. So we have 7y to the power of minus 3 plus 3 of y to the power minus 2 plus 5 of y to the power minus 1 plus 1 equal to 0. Now I'm going to multiply all the terms by y to the power of 3. And what we're going to get is 7 here, and this is plus 3y, and this one is plus 5y squared, and it's plus y cubed equal to 0. And rearranging, we'll be having y cubed plus 5y squared plus 3y plus 7 equal to 0. So that's it for part A. Let's go on to part B. On part B, the question goes, find the value of alpha to the minus 2 plus beta to the power minus 2 plus gamma to the power of minus 2. So using this important result, we can say this is equal to the summation of roots of the form alpha to the power minus 2. And this should be equal to the summation of roots of the form alpha to the power minus 1, and that's squared. And that's minus 2 of the sum of product of pairs of roots of this form. Now, here, the sum of roots of the form alpha to the power minus 1 is the sum of roots of this cubic polynomial equation that we formed in part A. So this will be minus b over a. B is the coefficient of y squared, so that will be minus 5 over 1. So we have minus 5 for that. So that's minus 5, and that's squared, and it's minus 2 of the sum of the product of pairs of the roots of this form is, in this case, c over a. C in this case is the coefficient of y, so that's 3 over 1, which is just 3. So if we simplify this, we'll be having 25 minus 6, and 25 minus 6 is 19. So that's the answer to part B. Let's go on to part C. On part C, the question goes, find the value of alpha to the power minus 3 plus beta to the power minus 3 plus gamma to the power of minus 3. So for this one, we should come out with some kind of recurrence relation for the roots of this cubic polynomial equation. So I'm going to take it down. That's y cubed plus 5y squared plus 3y plus 7 equal to 0. And I'll make y cubed subject, so y cubed is equal to minus 5y squared minus 3y minus 7. So here, since alpha to the power minus 1 and beta to the power minus 1 and gamma to the power minus 1 are roots to this cubic polynomial equation, if we add up the three, we'll be having this recurrence relation. That's the summation of roots of the form alpha to the power minus 3 is equal to minus 5 of the summation of roots of the form alpha to the minus 2, and that's minus 3 of the summation of roots of the form alpha to the power minus 1, and it's minus 21. So here, the sum of roots of the form alpha to the power minus 2 is what we got in part B, and that's 19. So we have 19 here, and it's minus 3 of the summation of roots of the form alpha to the minus 1. These are the sum of roots of this cubic polynomial equation we formed in part A. So that's minus 5, okay, minus B over A. So we have minus 5 here, and it's minus 21. So minus 5 times 19 is minus 95, and that's minus 3 times minus 5 is plus 15, and it's minus 21. And adding up this, we get the answer as minus 101. So that's what we get for part C. And that's it for question number 1. Question number 2. The sequence u sub 1, u sub 2, u sub 3, and so on is such that u sub 1 is equal to 1 and u sub n plus 1 is equal to 2 u sub n plus 1 for n is greater than or equal to 1. So on A they say, prove by induction that u sub n is equal to 2 to the power of n minus 1 for all positive integers n. So here the procedure remains the same. I am going to start by proving for n is equal to 1. So that's our best case. Okay? And for n is equal to 1, from this formula here, that will be u sub 1. And u sub 1 here is 2 to the power of 1 minus 1, which is equal to 1. Now u sub 1 is equal to 1, and that is what's been given originally in the information above. So this should be true. So I can say, hence, proved true for n is equal to 1. Next, I'm going to assume true for n is equal to k. So that means that I'll be having u sub k being equal to 2 to the power of k minus 1. So then I go on to n is equal to k plus 1 to see if this is going to be true given that n is equal to k. So when n is equal to k plus 1, we'll be having u sub k plus 1. And we know from the information given that u sub n plus 1 is 2 of u sub n plus 1. So that means that u sub k plus 1 should therefore be 2 of u sub k plus 1, just following the same formula here. And applying the assumption, we will be saying here, in place of u sub k, we will put 2 to the power of k minus 1. So it's 2 of 2 to the power of k minus 1 plus 1. So we now be having 2 of 2 to the power of k minus 2 plus 1. And multiplying 2 times 2 to the power k, we know that 2 is 2 to the power 1. So multiplying the 2, we get 2 to the power of k plus 1. And minus 2 plus 1 is minus 1. Now what we have here is showing us that the sequence formula is true also when n is equal to k plus 1. Just think of if you were going to replace n for k plus 1, that would be 2 to the power of n minus 1, which is the same form for the nth term formula here. So this is true. So I can say, hence proved true for n is equal to k plus 1. So for the concluding statement, I will say, if true for n is equal to k, then it must be also true for n is equal to k plus 1, as we have proved. And therefore, by the principle of mathematical induction, it is true for all positive integers n. So that is how we handle this first part. Then on part B, the question goes, deduce that u sub 2n is divisible by u sub n for n is greater than or equal to 1. Okay, so it's u sub 2n over u sub n, right? So what is u sub 2n? We can take this formula here and let's place it here. So u sub 2n means we're substituting 2n here, so it'll give us 2 to the power of 2n minus 1, and that's all over u sub n, which is 2 to the power of n minus 1. So we want to see if the two are divisible or not. Okay, now if you look at the numerator here, you can notice that it's actually a difference of 2 squares. It's like 2 to the power of n squared minus 1 squared, if we want to write it showing all the squares. And that's over 2 to the power of n minus 1. So this can be simplified to 2 to the power of n plus 1 of 2 to the power of n minus 1. And that's all over 2 to the power of n minus 1. So the two are divisible if we cancel out the 2 to the power n minus 1, and we are left with 2 to the power of n plus 1. So we are actually seeing that they are divisible, and that's how we do it. Question 3. Let s sub n be equal to 2 squared plus 6 squared plus 10 squared plus all the way to 4n minus 2 squared. On A, use standard results from the list of formula MF19 to show that s sub n is equal to 4/3 of n of 4n squared minus 1. So let's start with that. So the series that we got, that's s sub n, can be written in sigma notation as the summation from r is equal to 1 up to n of terms of the form, taking the form of the last term, 4r minus 2 all squared. Now we can simplify this to the summation from r is equal to 1 up to n of, expanding the brackets here, we'll be having 16r squared minus 16r plus 4. Now this is equal to the summation from r is equal to 1 up to n of 16r squared, and it's minus the summation from r is equal to 1 up to n of the form 16r, and it's plus the summation from r is equal to 1 up to n of 4. So we can also factor out 16 here, so 16 of the summation from r is equal to 1 up to n of the form r squared, and it's minus 16 of the summation of roots from r is equal to 1 up to n of the form r, and it's plus the summation from r is equal to 1 up to n of 4. So here, using these standard results, for r squared, that's a 1/6 of n plus 1 of 2n plus 1. And here it's minus 16. And for the sum of roots of the form R, we'll be having a half of n plus 1 like this. And it's plus 4 times n, so that will be 4n. So we can simplify this. Here, 16 times a sixth n is 8 over 3 of n. And that's of multiplying these two brackets, we are going to get 2n squared, and that's plus 3n, and that's plus 1. And that's minus, here 16 times a half n is minus 8n. And we're going to multiply that to n plus 1, so we have n plus 1 here, and it's plus 4n. So next we'll be having, expanding the brackets, 16 n cubed, and that's over 3, and it's plus, multiplying 8/3 of n times 3n, we'll be having 8n squared, and that's plus, multiplying 8/3 of n times 1 is just 8/3 of n, and that's minus 8n squared minus 8n, and that's plus 4n. So here I'll be having 16 over 3 of n cubed, and for 8n squared minus 8n squared we get 0. Then 8/3 of n minus 8n plus 4n will give us minus 4/3 of n. So here I can factor out 4/3 of n, and that will give me inside the bracket 4n squared minus 1. So this is what we get, and according to the question, that's what they want us to show. So here I'll say hence shown. Let's go on to part B. On part B, it goes express n over s sub n in partial fractions and find the summation from n is equal to 1 to capital N of terms of the form n over s sub n in terms of n. Okay, so here we are going to look for n over s sub n, which should be equal to n over, for s sub n, we are going to use this. That's 4/3 of n of 4n squared minus 1 like this. So let's simplify this. This is going to be equal to n divided by, and the denominator here, I'm going to write it as 4 of n of 4n squared minus 1 all over 3. And that's the same as n, which is n over 1, times inverting, we'll be having 3 over 4n of 4n squared minus 1. So here we can cancel out the n's, which means that we'll be having 3, and that's over 4 of 4n squared minus 1. Now this can also be expressed as 3 over 4 of 2n plus 1 bracket 2n minus 1, using the concept of difference of two squares. Now if we want to express this in partial fractions, we'll say this is equal to a over 2n plus 1 and plus b over 2n minus 1. So we're going to come out with an identity, which is 3/4 is equal to a of 2n minus 1 plus b of 2n plus 1. And here, if n is equal to a half, then on the left side we'll be having 3/4, and on the right side, substituting a half for n on this part, we will get 0. But if we substitute a half for n on this part, then we are going to get 2b. So here b will come out as 3/8. Then when n is equal to minus a half, then on the left side we'll be having 3/4, and that will be equal to, here if we substitute minus a half, we get minus 2a. But if we substitute minus a half for n on this part, then we get 0. So here A will come out as minus 3/8. So we basically have n over s sub n being equal to 3/8 of 1 over 2n minus 1, and it's minus 1 over 2n plus 1. So this is what we get for n over s sub n, substituting a and b into this. Now the question says, find the summation from n is equal to 1 up to capital N of n over s sub n. So we're going to use the method of differences there. So we are saying here the summation from n is equal to 1 up to capital N of the form n over s sub n, that will be equal to the summation from n is equal to 1 up to capital N of the form 3/8 of 1 over 2n minus 1, and that's minus 1 over 2n plus 1, like this. And here we'll be having 3/8, and that's off. Here, substituting n is equal to 1 into this, we will have 1 over 2 of 1 minus 1, which is just 1, and it's minus, substituting 1 here, we get a third, so it's minus a third. And substituting 2 into this, we will get 1 over 2 of 2 minus 1, which is 1 of 4 minus 1, that's a third, so that's plus a third. And substituting 2, we get minus 1 over 2 times 2 plus 1, which is 1 over 5. So this series will continue all the way to the last term. That's when n is equal to capital N. And when n is capital N, we'll be having 1 over 2 capital N minus 1, and it's minus 1 over 2 of capital N plus 1. So this is the series here expanded. Now, by the method of differences, minus a third will add up to a third to give us 0, and so will minus a fifth, it will add to a fifth, which is along the way in the series. So all the terms that are right in between will add up to give us 0. So we'll be left with 1 and minus 1 over 2n plus 1 inside the bracket. So we can say this is equal to 3/8 of 1 minus 1 over 2n plus 1. So this is the answer right here. Let's go on to the last part, that's part C. Deduce the value of the summation from n is equal to 1 to infinity of the form n over s sub n. So I can say this is equal to the limit as n approaches infinity of 3/8 of 1 minus 1 over 2n plus 1, like we got right above. That's for the summation of roots up to n. So here, as n approaches infinity, this fraction here will turn towards 0. So it's like we have 3/8 of 1 minus 0, which basically is going to give us 3/8. So that's the answer right here. And that's it for question number 3. Question number 4. The matrix A is given by A is equal to the 3 by 3 matrix with elements k0, 2, 0 minus 1 minus 1, and 1, 1 minus k, where k is a real constant. So on A, show that A is non-singular. Now here we know that a singular matrix has a determinant 0. So let's find the determinant here. So we'll say the determinant of A is equal to, and we start with k, and we close out row and column. So we'll be having the determinant of minus 1, minus 1, 1, and minus k. Then we go on to 0, And we know that multiplying anything by 0 gives us 0, so we're going to skip that. So we go on to 2 and we close out row and column. So we'll be having plus 2 times the determinant of 0 minus 1, 1 and 1. So this is k of, then minus 1 times minus k is k, and it's minus 1 times 1, so it becomes plus 1 here. And it's plus 2 of 0 times 1 is 0, and it's minus 1 times 1, which is minus 1, so we just get plus 1. So we have k squared plus k plus 2 for the determinant. Now for what we've got, let us consider the discriminant. That's b squared minus 4ac. And for this one, we will get 1 squared minus 4 of 1 of 2, which is 1 minus 8, which comes out as minus 7. Now minus 7 is less than 0, which means to us that there are no real values of k for which k squared plus k plus 2 is equal to 0. So therefore, we can say that A is non-singular. So let's go on to part B. The matrices B and C are given by B is equal to 0 minus 3 minus 1 3 and 0 0, and C is equal to minus 3 minus 1 1 and 1 1 2. It is given that CAB is equal to the 2 by 2 matrix with elements minus 2, minus 3 over 2, minus 1 and minus 3 over 2. So they say here on B, find the value of K. So here we've been given that CAB is equal to this 2 by 2 matrix. So let's start by finding CAB. Now the matrix C is this matrix with elements minus 3, minus 1, 1, then 1, 1, and 2. And it's multiplying the matrix A with elements K, 0, 2, 0, minus 1, minus 1, then 1, 1, and minus K. Then the matrix B is the matrix with elements 0, minus 3, minus 1, 3, then 0, 0, like this. So we want to multiply this 3. Let's start with the first two. So for the first two matrices, I'll multiply row by column. So that's minus 3 times k, which is minus 3k, and it's plus minus 1 times 0, which is 0, and it's plus 1 times 1, which is plus 1. Then this row and this column, that will be minus 3 times 0, which is 0. Then minus 1 times minus 1, that's 1. Then 1 times 1 is 1. So we have 1 plus 1 for this, which should be 2. So I'll just write that down as 2. Then we have this row times this column. So minus 3 times 2 is minus 6. And it's plus minus 1 times minus 1, which is plus 1. Then plus 1 times minus k, which is minus k. So minus 6 plus 1 is minus 5. So here we have minus 5 minus k. So let's have it like that. So minus 5 minus k. Next we go on to this row and this column. So 1 times k is k. Then 1 times 0 is 0. And it's plus 2 times 1, which is 2. So we have k plus 2 here. Then this row times this column, that's 1 times 0, which is 0, plus 1 times minus 1, which is minus 1, and it's plus 2 times 1, which is 2. Now minus 1 plus 2 is 1, so we just have a 1 here. Then this row times this column, that's 1 times 2, which is 2, and it's plus 1 times minus 1, that's minus 1, and it's plus 2 times minus k, which is minus 2k. Now 2 minus 1 is 1, so we'll be having here 1 minus 2k. So let's have it as 1 minus 2k. And all this is multiplying. Now the third matrix, 0 minus 3 minus 1, 3, 0, 0, like this. So now we continue multiplying. We are multiplying now the top row and the first column. So that's minus 3k plus 1 times 0, that's 0, plus 2 times minus 1, which is minus 2, and it's plus minus 5 minus k times 0, which is 0. So we are good. Then this row times this column, that's minus 3k plus 1 times minus 3, which gives us 9k minus 3. And it's plus 2 times 3, which is 6. And it's plus minus 5 times minus k times 0, which is 0. So 9k minus 3 plus 6 is like 9k plus 3. So let's have it like that as 9k plus 3. Then for the lower row and the first column, that's k plus 2 times 0, which is 0, plus 1 times minus 1, which is minus 1. Then 1 minus 2k times 0 is 0. So next, it's this row times this column. So it's k plus 2 times minus 3, which is minus 3k minus 6. And it's plus 1 times 3, which is 3. And it's plus 1 minus 2k times 0, which is 0. So minus 3k minus 6 plus 3 is like minus 3k minus 3. So that's minus 3k minus 3. Now, according to the question, CAB is equal to this 2 by 2 matrix. So I'm going to say it's equal to the matrix with elements minus 2, minus 3 over 2, minus 1, and minus 3 over 2. To find the value of k, I'm going to take this element on the first row, second column. So that's 9k plus 3 is equal to this element, which is also on the first row and second column. That's minus 3 over 2. So if I multiply all the terms by 2, I'll be having 18k plus 6 is equal to minus 3. And if I subtract 6 from both sides, I'll be having 18k being equal to minus 9. And if I divide both sides by 18, I get k coming out as minus a half. So this is how we find the value of k. Let's go on to part C. Find the equations of the invariant lines through the origin of the transformation in the xy plane represented by CAB. Okay, so here for the invariant lines, we're going to say the matrix CAB, which is minus 2, minus 3 over 2, minus 1, minus 3 over 2, multiplied by xy, will give us the image x dash y dash. So let's simplify this. So this row times the column will be having minus 2x and minus 3 over 2 times y, that's minus 3 over 2y. Then this lower row times the column, we get minus x, and it's minus 3 over 2y. And that's all equal to x dash y dash. So now we're saying, since the lines are passing through the origin, they should take the form y is equal to mx. So for the equations that I'll extract from this, I am going to substitute mx for y. So for the first equation, it's going to be minus 2x minus 3 over 2y, but in place of y, I'm going to put mx, so mx, and that's equal to x dash. And for the second equation, I'll be having minus x minus 3 over 2y, but in place of y again, I'll put mx, and that's equal to y dash. Now, we know that these lines are invariant, so the line is invariant, and it therefore means that the image formed under the transformation should also take the form y dash is equal to m of x dash. So here, y dash, therefore, is minus x minus 3 over 2 of mx, and it's equal to m of x dash. X dash here is minus 2x minus 3 over 2 of mx, So that's minus x minus 3 over 2 of mx equal to minus 2 of mx minus 3 over 2 of m squared x. Now all the terms have x on them, so if we divide both sides or divide all the terms by x, then the x will be eliminated. So we'll be having minus 1 minus 3 over 2 of m being equal to minus 2m, and it's minus 3 over 2 of m squared. Now I'll multiply all the terms by 2. So we'll be having minus 2 minus 3m equal to minus 4m minus 3m squared. Now I'll take everything on the right side to the left side. So minus 3m squared becomes 3m squared. And minus 4m adds up to minus 3m to give us m. And we have the minus 2 here already, so it's all equal to 0. Now we can solve for m by factorizing. So I'll factorize this. So we have 3m here and we have m. And we should be having a 2 here and a 1. Then minus here, then plus. So this is the quadratic equation in m factorized. So therefore it's either 3m minus 2 that's equal to 0 or m plus 1 that's equal to 0, where we'll get the value of m coming out as 2/3 and m here coming out as minus 1. So we now have the two possible values of m, and we are saying that the invariant lines through the origin take the form y is equal to mx. So here we are saying since y is equal to mx, the invariant lines through the origin are going to come out as y is equal to 2/3 of x. That's substituting 2/3 for m, and y is equal to minus x, substituting minus 1 for m. So this is what we get as our answers. So that's it for part C, and we're done with this question. Question 5. The curve C has polar equation r is equal to a tan theta, where a is a positive constant and theta ranges between 0 and a quarter pi. So on A, sketch C and state the greatest distance of a point on C from the pole. Now to make the sketch, let us consider this polar plane. We have values of theta ranging between 0 and a quarter pi. So we're going to have 3 intervals within this range, which means that I'll divide pi over 4 by 3 to get pi over 12. So we're going to be going in pi over 12 increments. So this should be pi over 12, and this should be 2 pi over 12, which is pi over 6. For the table of values, substituting 0 into the equation, we get r coming out as 0. When theta is equal to pi over 12, r is 0.3a. If we substitute pi over 6 for theta into the equation, we get r coming out as 0.6a. And lastly, if we substitute pi over 4 into the equation, we get r coming out as a. So this is the table of values. And for the r values on the plane, I'll go in 0.3a intervals. So that's 0, 0.3a, 0.6a, 0.9a, and 1.2a. So we can now plot the points. Let's start with the point 0, 0, which is this point here. When theta is equal to pi over 12, r is 0.3a, so the point should be this one. When theta is pi over 6, r is 0.6a, so this is the point. And when theta is equal to pi over 4, r is a, which is this point here. So if we join the points, the curve will come out like this. So let's put that on the paper. So we have the initial line here, theta is equal to 0. And we're going to be having the line theta is equal to pi over 4, which is this line here. So the pole is right here, and so the graph was coming out to be like this. So that's how we make the sketch. Now, another part of the question goes, state the greatest distance of a point on C from the pole. Now, the point farthest from the pole is this point here. And the greatest distance from the pole is this distance here, which I want to call R. Now, this is the value of R when theta is equal to pi over 4. So we're saying here, R is equal to A tan pi over 4. Tan pi over 4 is 1, therefore R is equal to A. So the greatest distance from the pole is A. Let's go on to part B. On part B, they say, find the exact value of the area of the region bounded by C and the half line theta is equal to 1/4 pi. So here, the area that we are looking for is this area here. Now, to find the area bounded by the graph, we use the formula integral from alpha to beta of half r squared with respect to theta. In this case, area will be the integral from 0 to pi over 4 of half of r squared. Now, r is A tan theta, so we will have here A tan theta whole squared, and that's with respect to theta. So this will be the integral from 0 to pi over 4 of half of A squared tan squared theta with respect to theta. And I can take out the half A squared, so it will be half A squared of the integral from 0 to pi over 4. And as for tan squared theta, I'll use the identity to say it's equal to sec squared theta minus 1, and that's with respect to theta. So next, I'll be having half A squared, and now we can integrate sec squared theta. Now, for the integral of sec squared theta, if we go to the list of formulae, under differentiation, you find that if f of x is tan x, then f prime of x, which is the derivative, is sec squared of x. Which means if we do the reverse, which is integration, if we integrate sec squared x, we should get tan x. So here, if we integrate sec squared theta, we should get tan of theta. And that's minus integrating 1 with respect to theta gives us theta. And that's for values from 0 to pi over 4. So from here, we'll be having half A squared. And substituting pi over 4 for theta, we'll be having that as tan of pi over 4. And that's minus pi over 4. And it's minus, substituting 0 for theta, that will be tan 0 minus 0, which is just 0. So here I'll now be having half A squared of tan pi over 4 is 1, and it's minus pi over 4. So this is what we get as the answer. That's the area here. Let's go on to part C. On part C, they say, show that C has Cartesian equation y is equal to x squared over root of a squared minus x squared. What they want us to do here is to convert the polar equation r is equal to a tan theta into Cartesian form. So let's do that. Now we are saying r is a tan theta, so r is a, and in place of tan theta, I'll use sine theta over cos theta. And if we multiply both sides by cos theta, then we'll be having r cos theta is equal to a sine theta. From here, we can multiply both sides by r, so that on the left side, we'll be having r of r cos theta, and on the right side, we'll be having a of r sine theta. Now we know that r is the square root of x squared plus y squared, and that's times r cos theta, which is x, and it's equal to a of r sine theta, which is y. Now from this stage, I'll square both sides, and squaring both sides means we'll be having x squared plus y squared, and that's of x squared, and that's equal to a squared y squared. And if we multiply x squared into the bracket, we'll be having x power 4 plus x squared y squared equal to a squared y squared. Now what we are seeking to do is to make y subject. So in order for us to do that, I'll have the terms in y squared on one side of this equation. So we'll be having a squared y squared minus x squared y squared equal to x to the power of 4. And we can factor out y squared to get a squared minus x squared in the bracket is equal to x to the power of 4. And dividing both sides by a squared minus x squared, we'll be having y squared left on the left side, and on the right side we'll be having x power 4 all over a squared minus x squared. And the last step here is I will square root both sides, and if we do, then we'll be having on the left side y, and on the right side x squared over the square root of a squared minus x squared. And that is the expected result. So I'm going to say here, hence shown. On the last part, that's part D, they say, using your answer to part B, deduce the exact value of the integral from 0 to half a root 2 of x squared over root of a squared minus x squared with respect to x. Now, to understand this question, let's go back to the sketch of the curve C. So I'll take it here and place it here. So what we have right here is r is equal to a tan theta. So that is the polar equation for this curve C. Now the Cartesian equation for the sum graph is y is equal to x squared over root of a squared minus x squared. And if we're integrating from 0 to half a root 2, this definite integral means we're looking for area under the Cartesian form of the graph. So we say here we're looking for this area. That's the area under the Cartesian form of the graph. So this point here is 0, and this point is half a root 2. Now to find this area shaded in green, we can start by finding the area under the triangle, which is half times the base times the height. So it's half times the base is half a root 2, or we can consider that this angle is pi over 4, which means that the base is hypotenuse cos of the angle. So it'll be r, which is a in this case. So that'll be a cos of pi over 4 times the height, which is hypotenuse sine of the angle, which is a sine of pi over 4. And that's minus the area shaded in gray, which is the area bounded by the polar graph. And we got that earlier on part B as half a squared of 1 minus pi over 4. So let's have that. So it's minus half a squared of 1 minus pi over 4. So this is what will give us the shaded area in green. So let's simplify this. So we'll be having half times a cos pi over 4, which is root 2 over 2a, and it's times a sine pi over 4, which is root 2 over 2a, and it's minus, here we'll be having half a squared, and then minus half a squared by minus pi over 4 will give us plus pi over 8 a squared. So we can simplify this a little bit more. At the top we'll be having 1 times root 2a times root 2a, which is 2a squared, and it's over 2 times 2 times 2, which is 8, and it's minus, here half a squared is just half a squared, and it's plus pi over 8 of a squared. Now this is a quarter a squared. So a quarter a squared minus half a squared will give us minus a quarter a squared. And we have pi over 8 a squared. So we can factor out here a quarter a squared. And a quarter a squared into pi over 8 a squared, we get half pi or pi over 2. And dividing a quarter a squared into minus a quarter a squared, we get minus 1. So the answer comes out like this. Question number 6. The curve C has the equation y is equal to 10 plus x minus 2x squared all over 2x minus 3. On A, find the equations of the asymptotes of C. So here I'll start with the vertical asymptote. For the vertical asymptote, I will set the denominator to 0. So here I'll say 2x minus 3 equal to 0. And here x will come out as 3 over 2. So this here is the equation of the vertical asymptote. Now the other asymptote is going to be an oblique asymptote. Determine that by considering that degree of the numerator is 1 greater than the degree of the denominator. So to find the oblique asymptote, all we need to do is to divide 2x minus 3 into the numerator. So let's do that. That's 2x minus 3, and we're going to divide that into the numerator. I'll write it as minus 2x squared plus x plus 10. Now we divide 2x into minus 2x squared, and we get minus x, and multiply minus x by minus 2x minus 3. So that's minus 2x squared plus 3x. And I'm going to subtract. So minus 2x squared minus 2x squared is 0. Then x minus 3x is minus 2x. Then we bring down the 10. Then I'll divide again 2x into minus 2x, and I get minus 1. So that's minus 1. And I multiply minus 1 times this divisor to get minus 2x plus 3. Then I subtract. Minus 2x minus 2x is 0, and then 10 minus 3 coming out as 7. But what we're concerned with is the quotient here, which is minus x minus 1. So we are saying here the oblique asymptote is y is equal to minus x minus 1. So that's the equation of the oblique asymptote. Let's go on to part B. On part B, the question goes, show that C has no turning points. So here we're going to say at stationary point, dy by dx is equal to 0. And here for dy by dx, it is going to be equal to the denominator, which is 2x minus 3, multiplying the derivative of the numerator, which comes out as 1 minus 4x. And it's minus the numerator, which is 10 plus x minus 2x squared, multiplying the derivative of the denominator, which is 2. And that's all over the denominator squared, which is 2x minus 3 squared. So this is going to be equal to, expanding these brackets, we will get minus 8x squared plus 14x minus 3. That's by expanding these two brackets. And it's minus, expanding this bracket, multiplying by 2, then we'll be getting 20, and it's minus 2x, and it's plus 4x squared. And that's going to be equal to 0. And it comes out like this after we've multiplied both sides by the denominator. So let's simplify it from here. So we'll be having, for the terms in x squared, minus 8x squared plus 4x squared, which is minus 4x squared. And 14x minus 2x is plus 12x. Then we have minus 3 minus 20, which is minus 23, and that's equal to 0. And this can be rewritten as 4x squared minus 12x plus 23 equal to 0 by multiplying both sides by minus 1. Now, we want to see if we have any real values satisfying this equation. So for the discriminant, b squared minus 4ac, then we'll be having it as minus 12 squared minus 4 of 23. Now minus 12 squared is 144, and it's minus 4 times 4 times 23 gives us 368. And 144 minus 368 gives us minus 244, which is less than 0. And because of that, it means we have no real values satisfying this equation, and therefore we can make the conclusion that there are no turning points on the curve. Let's go down to part C. On part C, the question goes, sketch C, stating the coordinates of the intersection with the axis. Okay, so here I'll have the axis. So this is y and this is x. And we have the origin right here. Let's put in the asymptotes. We have two asymptotes. The vertical asymptote is x is equal to 3 over 2. So let's have that. So it intercepts at 3 over 2. Then for the oblique asymptote, it has the equation y is equal to minus x minus 1. So for that one, it's a line with a negative gradient intercepting the y-axis at minus 1. So this here is the oblique asymptote right here. Now considering that there are no turning points on this curve, then we know that the graph is going to come out like this. And the other piece like this. So this is how the graph comes out like. Okay, so we have also to state the coordinates of the intersections with the axis. So let's start with the x-intercepts. So x-intercepts, and these occur when y is equal to 0. So here, considering the original equation, I'm going to equate it to 0, such that I'll be having the equation 0 is equal to 10 plus x minus 2x squared, like this. So I can factorize this, and we will get 5 minus 2x and 2 plus x here, which therefore will give us x coming out as 5 over 2 or minus 2. And therefore the intercepts with the x-axis are at 5 over 2, 0, and at minus 2 and 0. So this point here is the point minus 2, 0, and this point here is the point 5 over 2 and 0. And also we need the intercept with the y-axis, and that happens when x is equal to 0. So we are saying here for the y-intercept, x is equal to 0, and when x is equal to 0 here, all these terms become 0, and we're left with y coming out as minus 10 over 3. So therefore the coordinates at the y-intercept will be at 0 and minus 10 over 3. So we can have that for the y-intercept here, that's 0 and minus 10 over 3. So that's it for this graph. Let's go on to part D. On part D, it goes, sketch the curve with the equation y is equal to mod of the function here, and find in exact form the set of values of x for which the modulus of the function is less than 4. Okay, so here we will start with the modulus graph. So I'll use the graph that we sketched on part C. So here it is, and I'm going to paste it here. And for the modulus graph, we are going to reflect the part of the graph that is below the x-axis in the x-axis. So let's do that. So reflecting this part below the x-axis to the left, it should come out like this. And since it was intercepting at 0 and minus 10 over 3, it should now intercept at 0 and positive 10 over 3. And now for this part that is below again to the right, we'll reflect it in the x-axis and it should come out like this. So more like this. So I'm going to remove the part that is below the x-axis, and this becomes the modulus graph. So I'll put back the intercepts here. We've got 0, and here we have 3 over 2, and here we have 5 over 2, and here we have minus 2. So this is how the graph will come out to be like. Now the other part of the question goes, find in exact form the set of values of x for which the modulus of the function is less than 4. So here I'm going to draw the line y is equal to 4, which should be somewhere around here above 10 over 3, which is 3 and a third. So this is the line y is equal to 4. And I'm going to look for the intercepts with the graph. So for these two intersections with the graph, we are saying 10 plus x minus 2x squared over 2x minus 3 is equal to 4. And for these two other parts, we are saying minus of 10 plus x minus 2x squared over 2x minus 3 is equal to 4. This is where the reflected parts of the graph intercept with the line y is equal to 4. So let's solve these two equations for x. So for this first one here, we have 10 plus x minus 2x squared, and it will be equal to 4 of 2x minus 3. That's 10 plus x minus 2x squared equal to 8x minus 12. Now taking everything on the left side to the right side, we'll be having 2x squared, and that's plus 7x minus 22 equal to 0. And this can be factorized to 2x plus 11 bracket x minus 2. So we can get the values of x coming out as minus 11 over 2 and 2. Now we can also solve the other equation where we're going to be having 10 plus x minus 2x squared, and it's equal to minus 4 of 2x minus 3. So that's 10 plus x minus 2x squared equal to minus 8x plus 12. So taking everything on the left side to the right side, we will be having 2x squared minus 9x plus 2 equal to 0. So I can solve this using my calculator. So here I go to equation, then option 3 for quadratic, and I'll store 2 for a, so 2 and equals, then minus 9 into b and 2 into c. And the first root comes out as 9 plus root 65 over 4. So I'm saying here x comes out as 9 plus root 65 over 4. And the second root comes out as 9 minus root 65 over 4. So that's and 9 minus root 65 over 4. So we now have the 4 intercepts with the graph. So the first set of values for which the modulus graph is less than or below the graph of y is equal to 4 is between this point and this point. So we say this is between minus 11 over 2 and 9 minus root 65 over 4. And also between this point and this point, that's where the modulus graph is below that of the graph y is equal to 4. So that's between 2 and 9 plus root 65 over 4. So these two give us the solution. And that's it for this question here. Question number 7. The lines L1 and L2 have equations r is equal to minus 5j plus lambda 5i plus 2k and r is equal to 4i plus 2j minus 2k plus mu of j plus k, respectively. The plane pi contains L1 and is parallel to L2. So on A, find the equation of pi, giving your answer in the form ax plus by plus cz equal to d. So here in this case we've got a plane, and the plane contains the line L1 and also is parallel to the line L2. So in order for us to find the equation of the plane pi, we'll need to find the normal to the plane. So we'll make use of the direction vectors of L1 and L2, so we can translate L2 to the plane and look for the normal. So here the equation of the plane, we're going to have it in the form r dot n is equal to d, where n is the normal. So for the normal n, we'll do cross product with the direction vectors of L1 and L2. The direction vector of L1 in column vector form is going to be 5, 0, 2. And it's cross multiplying the direction vector of L2, which is j plus k, but in column vector form, that's 0, 1, 1. So we have 0, 1, 1 here. So this is equal to, and here I'll close out 5 and 0. And then I'll say 0 times 1, which is 0, and it's minus 1 times 2, which is minus 2. Then I'll close out the middle elements. So 5 times 1 is 5, and it's minus 0 times 2. So we'll just have 5, but there has to be a minus on it, so it'll be minus 5. Then I'll close out the last elements 2 and 1. So I'll say 5 times 1, which is 5, and it's minus 0 times 0. So we'll just be having 5 here. So what we got here is the normal to this plane. Next, I'll need to find d, and we can find d by saying d is equal to a dot n, where a is any point on the plane and n is the normal. So in this case, we can say this is equal to, and a point on the plane, we can take minus 5j, which is 0, minus 5, 0 in column vector form, and it's dot n, which we got to be minus 2, minus 5, 5. And we can simplify this by multiplying 0 times minus 2, which is 0, and it's plus minus 5 times 5, which is 25, and it's plus 0 times 5, which is 0, and that gives us 25. So here the equation of the plane is r dot n, which we got to be minus 2, minus 5, 5, and it's equal to d, which is 25. And in the form ax plus by plus cz equal to d, that will be minus 2x minus 5y plus 5z equal to 25. So this is the answer right here. Let's go on to part B. On part B, find the distance between L2 and pi. Now if we consider that the line L2 is parallel to the plane, the distance between L2 and pi is like the perpendicular distance between a point on the line L2 and the plane. Now to find the perpendicular distance of a point x1, y1, z1 and a plane ax plus by plus cz equal to d, we can use this formula here. Now the point on L2 is going to be, considering L2 here, the point is supposed to be 4, 2, and minus 2. And for the equation of the plane pi, we got it to be minus 2x minus 5y plus 5z equal to 25. So we can apply the formula here to say d is equal to, and for ax1, that will be minus 2 times 4. So minus 2 times 4. and it's plus by, which is minus 5. So I have minus 5 here, times 2, and it's plus 5 of minus 2, and it's plus d, and d in this case will be minus 25 if we take it to the left side. So it's minus 25, and that's over the square root of a squared plus b squared plus c squared, which is minus 2 squared plus minus 5 squared plus 5 squared. Now the numerator is under modulus, so we shouldn't forget that. So let's simplify this. So we'll be having here on the numerator minus 2 times 4, which is minus 8, and it's minus 5 times 2, so that's minus 10, and then that's plus 5 times minus 2, which is minus 10, and we have minus 25. And that's over the square root of minus 2 squared, which is 4, plus minus 5 squared, which is 25, plus 5 squared, which is 25. Now minus 8 minus 10 minus 10 minus 25 is minus 53. And the absolute value for that is 53. And it's over here the square root of 4 plus 25 plus 25 is like the square root of 54. Now 53 divided by 54, let's have that. 53 divided by root 54 is 7.2123 SF. So the answer comes out as 7.21. So that's how we do it for part B. Let's go on to part C. The point P on L1 and the point Q on L2 are such that PQ is perpendicular to both L1 and L2. So on C, show that P has position vector 55 over 27i minus 5j plus 22 over 27k, and state the vector equation of PQ. So the situation we have right here is like this, where we have the two lines L1 and L2, and we have a point P on L1 and a point Q on L2, and PQ is perpendicular to both L1 and L2. So according to the question, we want to show that P has the position vector like this one. Now here we're going to find the vector PQ, and we know that PQ is OQ minus OP. Now OQ, which is this point, has the form for some value of mu 4, 2 plus mu, and minus 2 plus mu, and it's minus OP. Now OP for some value lambda should be 5 lambda minus 5 and 2 lambda. So this is going to give us 4 minus 5 lambda, 2 plus mu minus minus 5, which is 7 plus mu. Then minus 2 plus mu minus 2 lambda, that's minus 2 plus mu minus 2 lambda. So this is what we have for PQ. Now since PQ is perpendicular to both L1 and L2, we know that the dot product of PQ, which we got to be 4 minus 5 lambda, 7 plus mu, and minus 2 plus mu minus 2 lambda, is dot product with the direction vector of L1, which is 5, 0, 2, should give us 0. So that's 5 of 4 minus 5 lambda, and it's plus 0 times 7 plus mu, so that's 0, and it's plus 2 of minus 2 plus mu minus 2 lambda, and that's equal to 0. So that's 20 minus 25 lambda minus 4 plus 2 mu minus 4 lambda equal to 0. Now 20 minus 4 is 16, and we have minus 25 lambda minus 4 lambda, which is minus 29 lambda, and it's plus 2 mu, and it's equal to 0. So minus 29 lambda plus 2 mu is equal to minus 16. So let's call that equation 1. Now again, the dot product of PQ, which is 4 minus 5 lambda, 7 plus mu, and minus 2 plus mu minus 2 lambda, with the direction vector of L2, which is 0, 1, 1, should give us 0. So here, 4 minus 5 lambda times 0 is 0. Then 7 plus mu times 1 is just 7 plus mu. Then minus 2 plus mu minus 2 lambda multiplied by 1 is just minus 2 plus mu minus 2 lambda equal to 0. So 7 minus 2 is 5, and mu plus mu is 2 mu, and it's minus 2 lambda, and it's equal to 0. So we can write that as minus 2 lambda plus 2 mu is equal to minus 5. And I'm going to call that equation 2. Now we can solve equation 1 and equation 2 simultaneously. Okay, and we can do that by subtracting equation 1 minus equation 2. That's by the elimination method. So minus 29 lambda minus minus 2 lambda will give us minus 27 lambda. Then 2 mu minus 2 mu is 0, so these two are eliminated. Then minus 16 minus minus 5 gives us minus 11. So lambda comes out as 11 over 27. Now here, since we got the value of lambda, let's find OP. Because the question here was saying, show that P has position vector this. So the position vector of P is OP. And remember we said that OP has the form 5 lambda minus 5 and 2 lambda. So let's have that OP is 5 lambda minus 5 and 2 lambda. And since lambda is 11 over 27, that will be 5 of lambda, which is 11 over 27, then minus 5, then 2 of 11 over 27. And this is equal to 55 over 27 minus 5 and 22 over 27. And we can write that in IJK notation as 55 over 27I minus 5J, and it's plus 22 over 27K. So this is actually what they wanted us to come out with, exactly like this. So I'll say here, hence shown. So we're done with that first part. Then the question also goes and state a vector equation for PQ. Now we got PQ to be this. So let me take that. So PQ is equal to, and this is the form of PQ. Now the value of lambda, we got it to be 11 over 27. And the value of mu, we hadn't calculated that, but we can still find it here. Since we gotten lambda to be 11 over 27, and one of the equations is this is minus 2 lambda, which I can write as minus 2 of 11 over 27, and it's plus 2 mu equal to minus 5. Then 2 mu will be equal to minus 5 plus 22 over 27. So 2 mu is equal to, so here we are saying minus 5 plus 22 over 27, and we're getting that as minus 113 over 27. So that's minus 113 over 27. So mu, we will divide both sides by 2. So I'll say divided by 2. And that's minus 113 over 54. So minus 113 over 54. So this is mu. So equal to minus 113 over 54. Okay, so for PQ, the direction vector of PQ then is 4 minus 5 lambda, which is 4 minus 5 of 11 over 27. And it's 7 plus mu, which is 7 plus minus 113 over 54. And it's minus 2 plus mu, which is minus 113 over 54. And it's minus 2 of lambda, which is 11 over 27. So this here is PQ. So let's simplify it. 4 minus 5 of 11 over 27. Let's calculate that. So that's 4 minus 5 of 11 over 27. And we get 53 over 27. And we have 7 minus 113 over 54. So let's have that. 7 minus 113 over 54. And that's 265 over 54. Then the last one. On the last one we have minus 2 minus 113 over 54. And it's minus 2 of 11 over 27. So we get minus 265 over 54. Now what we got here can be simplified. Since it's just a direction vector, we can factor out 53 over 54. And if we do that, dividing 53 over 27 by 53 over 54, we get 2. And dividing 265 over 54 by 53 over 54, we get 5. And dividing minus 265 over 54 by 53 over 54, we get minus 5. So we're going to use this vector 2, 5, minus 5 as the direction vector of PQ. So we are saying for the line, vector equation of the line PQ, it should be R is equal to, then we need a point on the line PQ. Now we can take OP as a point on the line, which is 55 over 27, then minus 5, then 22 over 27. So that's a point on the line, and it's plus K of the direction vector of PQ, which we can take 2, 5, and minus 5. Now we can write it better still as here. For this one, we can factor out 1 over 27 and have 55 and minus 135 and 22 here. And it's plus K of 2, 5, minus 5. And what we have here is the vector equation of the line PQ. And that's it for this question here.